Hello and welcome to lecture 14 for the graduate course ECE 254B, Parallel Processing. In this lecture, I will talk about sorting and routing on hypercubes. In other words, we take the hypercube architecture and discuss how you can sort data on this architecture and how you can solve routing problems. In the same way that we did for meshes and torus networks, we now do the discussion of routing and hypercube architecture. Now, in the course of this discussion, we will learn about an important fact about limitation of oblivious routing algorithms. We'll see that in the worst case, oblivious routing algorithms behave miserably in terms of performance. And we show that bitonic sorting, which is a way of sorting, a method of sorting, is a good match to the hypercube architecture. Okay, so let's get started. First, a refresher about the hypercube architecture. Here I've shown at the top of the slide a three-dimensional or 3D hypercube, or 3-cube for short, with nodes. There are 8 nodes, 2 to the q nodes, 8 nodes in this case. Node labels of 3-bit binary numbers. And each node is connected to 3 neighbors, which we call those dimension 0, dimension 1, and dimension 2 neighbors. So, for example, if I take node 0, 0, 0, its dimension 0 neighbor, look at the 0th bit, is 0, 0, 1. We change that 0 to 1. Okay, so that's the dimension 0 neighbor. Its dimension 1 neighbor is 0, 1, 0. That's the dimension 1 neighbor. And its dimension 2 neighbor is 1, 0, 0, which is this node. So these are dimension 0 links. This broken line basically shows where dimension 0 links are. These are dimension 1 links, the vertical lines. And the red ones are dimension 2 links in this hypercube. Now, which of these dimensions we call 0, which one 1, which one 2, is completely arbitrary because hypercube is completely symmetric with respect to those dimensions. And this becomes apparent from this drawing down here. There's really no difference between those dimensions. So it's just a matter of convention and convenience to call one of the dimensions 0, the other one 1, the other 2. And in particular, when we talk about an ascend algorithm, where communication occurs in the order of dimensions from 0 to 2. So dimension 0 communication first, then dimension 1, then dimension 2. Even the complete symmetry, we can basically do it in any order. We can do dimension 0, dimension 2, dimension 1. Dimension 1, dimension 0, dimension 2, and so on, because the dimensions are completely symmetric. Okay, so remember that an ascend algorithm communicates along dimension 0, 1, all the way to q minus 1. So dimension number goes up in the course of the algorithm execution. A descend algorithm is one in which dimension number goes down. We start from the highest dimension and go down to dimension 0. Okay, so what do we mean by sorting on a hypercube? Remember that in the case of mesh and torus networks, uh, we started by numbering the processors. So if there are p processors, we numbered them 0 to p minus 1 in order to specify the sorted order. Okay. The same is true for the hypercube. So we number the processors 0 to 7 in this three-dimensional hypercube. And if we are sorting in ascending order, which is our default type of sorting, if I don't mention how we are sorting, it's always ascending order. The smallest value goes in processor 0, the next smallest in processor 1, the one after that in processor 2. So the order of the elements from smallest to largest is the same as the order of processor indices from smallest to largest. So the largest value in this example goes into processor 7. Okay, so here I'm assuming that I have 8 processors and 8 values to sort. More generally, I will have more values to sort. So there will be multiple values in each processor. Again, so a block of values that are the smallest goes here. The next block of values goes here, and so on. So what I just outlined is 1-1 sorting, meaning that there's one element per processor. And throughout the sorting algorithm, each processor maintains one element. The values just shift between processors. That's known as 1-1 sorting. Each processor starts with one element and ends up with one element after sorting. There are p items to sort and p processors. Then we also have kk sorting. That's when each processor starts with k elements and ends up with k elements. So the number of elements that we are sorting is k times p. So that the share of each processor, each of the p processors, is k elements. Okay, so for 1-1 sorting, Batcher's odd even merge or bitonic sort requires order log squared p time. There may be, although we don't know, order log p time deterministic algorithms, but such an algorithm is not known at present. Okay, neither we have proved that such an algorithm does not exist. So that's a mystery. Okay, we do have an order log squared p algorithm, which is the Batcher's method. I'll describe bitonic sort later during this lecture. Okay, so that's not bad, already pretty close to the potentially optimal algorithm order log p, even though nobody knows such an algorithm yet. For kk sorting, optimal algorithms known when n is much greater than p. So what do we mean by optimal algorithm? An optimal algorithm should take order n log n divided by p. Okay, n log n is the sequential sorting time, and divided by p means we have optimal speed up, order p speed up. Okay, so we have optimal deterministic algorithms for when n is greater than p, or when average running time is considered. In other words, we take a random instance of the sorting problem, and its running time will be optimal on average. Okay, so this dartboard basically shows the situation with regard to sorting algorithms. The bullseye right in the middle is an order log n deterministic algorithm for sorting with n processors, and such an algorithm is not known. Ideally, someday we may find it, although even if we find such an algorithm, there's a chance. We have seen optimal algorithms before that are nice theoretically, but they don't translate into practical solutions, practical algorithms. And it may well be the case if we someday find an order log n algorithm for the hypercube, it won't be practical. Okay, now we have all these other darts show that we have sort of tried different ways. So for example, the bitonic sorting is order log squared n, which isn't bad. It's a very simple algorithm to implement. We have, I'll just discuss a few of these. We have order log n randomized. So if we don't care about the worst case time, but the average time, then this is good enough. Uh, when n is much larger than p, we do have optimal algorithms that take order n log n divided by p time. Okay, so that's basically a practical instance of the problem, because usually we will have many more items to sort than there are processors. In 1990, somebody discovered this log n log n squared algorithm. So this isn't quite log n, it's off by this factor. And this factor is not very large because log n is a small number. And in fact, that was improved later to order log n log n. So this basically square was removed. So it's only a factor log n away from the absolute best possible. Potentially possible. We don't know if it's possible. Okay. So this is the situation. So I'm going to discuss bitonic sorting in detail. This is a very practical algorithm that requires order log squared n. So at this point, the pursuit of order log p time algorithm, in other words, p processors and p items to sort, is of theoretical interest only, because the practical algorithms that we have are good enough for the types of problems that we try to solve. Okay, so let's describe the bitonic sorting algorithm. What is a bitonic sequence? Well, to define bitonic sequence, let's first see what a monotonic sequence is. A monotonic sequence is a sequence that basically varies in one way, okay? So it goes up or goes down, but not both at the same time. So for example, this part of this sequence from 1 to this last 6 is monotonic. 1, 3, 3, 4, 6, 6, 6. So from one element to the next, we either go up or stay at the same value, but never go back down. So this part of the sequence 1, 3, 3, 4, 6, 6, 6 is monotonic. Similarly, this part of the sequence 6, 6, 6, 2, 2, 1, 0, 0 is also monotonic because it only goes down, never goes up. 6, 6, 6, stay the same. Go down to 2, stay the same. Go down to 1, go down to 0, stay the same. So we either from one element to the next, we go down, or we stay at the same value. That's monotonic. So a bitonic sequence is a sequence that starts by going up and then ends by going down. So this is sort of a graphical illustration. The sequence goes up to a certain point. Sometimes it stays the same, okay? And then it goes down. Again, sometimes it stays the same for a while. Okay, so this is a bitonic sequence. Up, then down. This is also a bitonic sequence. Down, then up. Okay, for a while it goes down up to a certain point, and then it goes up from that point. So it has basically two monotonic parts, a decreasing part and an increasing part. This one has an increasing part followed by a decreasing part. That's a pure bitonic sequence. Now, for the purpose of the algorithm that we develop, if you take a bitonic sequence, a pure bitonic sequence of the type I showed you there, then you cut off part of that sequence and attach it at the other end. we still call this a bitonic sequence, even though strictly speaking it's not bitonic, because here I've cut this portion and attached it at the other end. So this is basically rotation. I've rotated the sequence. Okay, so this sequence goes up, then goes down, then goes up again. So it's really not bitonic like this one is. But because our algorithms will work for such sequences, we consider these, we call these bitonic, even though strictly speaking they are not. So if you take a pure bitonic sequence, cut part of it, and attach it at the other end, it's still bitonic. Similarly for this one, I cut this section of the sequence and put it at the other end. In other words, I rotate the sequence. So rotate the left. So these values, everything moves to the left, and these values go to the other end. So any rotation of a pure bitonic sequence, we also call bitonic because our algorithms work for such sequences as well. Okay, so first we start by showing how a bitonic sequence can be sorted. Of course, every sequence that we want to sort is not necessarily bitonic, but this is our starting point. If a sequence is bitonic, like the one shown here, notice again that this one goes down, then up, then down. But because if I rotate this by cutting this part and putting it at the other end, it becomes a pure bitonic. I consider this bitonic as well. Okay, so here's how to sort a bitonic sequence. Imagine that this sequence is stored on a linear array of length n. So there are n numbers and they're stored on a linear array of length n. We take the values on the right half of the linear array and shift them to the left. So these values, starting from here all the way to the end, have been shifted to the left by n/2 cells. So this red dashed line is basically a representation of these values that were originally in the right half of the array. They are now here. Each processor in the left half has two values: its own original value, the black value, and the value that came from the right half, the red value. Now, each processor compares the two values, keeps the smaller of the two. So this value, this black value, and this red value are compared. The smaller value is kept, and the red value is sent back to the right half. The next processor keeps the black, sends the red value to the right. So up to this point, the red value is larger, so it ends up going to the right. And the black value is kept on this half. From this point, the red value is smaller, so the red values are kept here, and the black values, which are larger, are sent to the others. Okay? Now I want you to observe two properties of these two half sequences, which we have formed down here. First of all, every element of the left sequence is smaller than every element, smaller than or equal to every element of the right. That's by construction, okay, because we kept these smaller values on the left side and we send these larger values to the right side. Second, each of these half sequences is a bitonic sequence. So this is a bitonic sequence, and this is a bitonic sequence. That's easily proven. Okay? Now, because all the elements on the left side are smaller than all the elements, smaller than or equal to all the, if I sort the left side independently and the right side independently, the entire sequence will be sorted. So on a linear array, in order to implement, so assuming that we start with a bitonic sequence, we need this shift of n over 2 or p over 2, if we call the number of processors p, and then another shift by p over 2 to bring these larger values back to the right to get to this point. So running time for sorting a bitonic sequence of length p is p. So that's p over 2 movements plus p over 2 movements back. Then I have to sort these half-size bitonic sequences, and I recursively can apply the same algorithm. So a quarter of these elements will be shifted there, and then they'll be shifted back. So that's p over 2 time. And then similarly, the right half of the array independently tries to sort this part. Again, it will have p over 4 plus p over 4. So that's where the p over 2 term comes, and all the way down to 2. So in 2p minus 2 steps, okay, I'm able to sort a bitonic sequence on a linear array. Now, all the communications are unidirectional in this process because in the first phase of the algorithm, things move to the left, and in the second phase of the algorithm, things move to the right. So 2p minus 2 unidirectional communication step. Now, in a linear array, we discussed the sorting algorithm, the odd-even transposition, that required p steps. And if you basically consider unidirectional steps, it requires 2p steps. Okay, so this is of the same, roughly of the same order of complexity as linear array sorting using the odd-even transposition sort, except odd-even transposition sort is applicable to any sequence, not just bitonic sequences. So this is actually not a great result because we are spending this roughly the same amount of time as general sorting on a linear array. Okay, so let's not dwell on this. What about sorting an arbitrary sequence on linear array using this bitonic sorting concept? Well, if I sort the first half of the array from left to right, and then sort the right half of the array from right to left. So here you see 3, 5, 7, 9, 10, 12, 14, 15 is sorted from left to right. And 1, 2, 4, 6, 8, 11, 13, 16 is sorted from right to left. The resulting sequence is bitonic by definition because the sequence goes up and then goes down. Therefore, I can sort this sequence in 2p minus 2 steps. Okay? Now, how do I sort the left half and the right half of the array? I basically recursively apply the same concept. Sort the first quarter from left to right, sort the second quarter from right to left. This is a bitonic sequence, and so on and so forth. Or going from bottom up, basically I sort pairs of elements, 5 and 9, 15 and 10, which becomes 10, 15 when I sort in this order, 3, 7, 12, 14, 1, 8, 4, 13, and so on. So I sort pairs of elements. Then I sort 4 elements by merging, basically sorting this bitonic sequence that I formed there. Then I sort this bitonic sequence of length 8, and so on. So sorting time for a p processor array is the sorting time for p over 2. That's basically forming these half sequences, sorted sequences, plus bitonic sort. And if I plug the bitonic sorting time here, 2p minus 2, I get 4p minus 4 minus the smaller term. So roughly 4p. Actually, we didn't make progress over the odd-even transposition sort because odd-even transposition sort requires 2p steps, whereas this one requires roughly 4p steps if I ignore the lower order two. But this was just a tool to describe the idea of Bytonic sequence sorting. So here's visualization of the Bytonic sequence sorting algorithm. So here is a sequence on the linear array. Values in the left half are shown in red. Values in the right half are shown in blue. But this is just, an arbitrary order of elements. Okay, some values are small, some are large, and so on. So the height of the bar represents the value. So I sort the left half of the array from small to large. I sort these values. I sort the right half of the array from right to left. So the smallest value goes there, the next smallest goes here. Now I have a Bytonic sequence. How do I sort a Bytonic sequence? I ship these values from the right half of the array to the left half. You see the blue values have gone to this side. Now each processor has two values stored in it. Keep the smaller of the two values, in this case the red one, and ship the larger of the two values to the right half. Okay, so up to this point the red values are smaller, so they're kept, and the blue values are shipped back. In these two positions, the blue values are smaller, so they're kept, and the red values are shifted back. Now I have a Bytonic sequence here and a Bytonic sequence here. So increase, then decrease. This one decreases, then increases. If I sort these two Bytonic sequences independently, the entire sequence will be sorted. So this is sort of visualizing what happens. So why is Bytonic sorting a good fit to the Hypercube? Well, it is a good fit because, see, I take half of the values on this side and ship them to the other side. Remember, in the Hypercube, if I have a Q cube, it consists of two Q minus 1 cubes, and the corresponding elements of the two Q minus 1 cubes are connected to each other. So the processor holding this value is connected to this one. The one holding this value is connected to this one. So this shipping of values from the right half to the left half takes just one step, and shipping the values back also takes one step. So in a constant number of steps, these comparisons are performed. So this part of the algorithm, going from here to here, takes a constant number of steps. Okay, so the time for sorting a Bytonic sequence on the Q-dimensional hypercube is the time for sorting a Bytonic sequence on the Q minus 1 dimensional hypercube plus a constant. This constant is basically the time needed for bidirectional communication, sending a value over and sending a value back. Okay, so Bytonic sequence sorting will require logarithmic log p time or q steps. Because if I unroll this, all these one terms, there will be q of them. Okay, so the time for Bytonic sequence sorting is q bidirectional communication steps, or 2 times q unidirectional communication steps. So this is the algorithm for the hypercube. For L is the dimension along which we communicate from q minus 1 down to 0. So this is a descent algorithm. We go from the highest dimension to the smallest dimension. Each processor, this is basically all the processors, do the following. If XL, if bit L, the processor ID is 0, then the processor gets a value Y, which is basically the value V in its dimension L neighbor. The value V in the dimension L neighbor. Then keep the minimum of your own value. Oops. The minimum of your own value, V of X, and the value you just got from your dimension L neighbor, which we called Y. Send the larger of the two values to your dimension L neighbor. Okay, you see how simple this algorithm is, but this only sorts a bitonic sequence. Okay, it's not a general sorting algorithm. So we need Q steps to sort a bitonic sequence. Okay, where do we get a bitonic sequence? Well, we do half sorts. In other words, if I want to sort on this hypercube, I sort in this half of the hypercube in ascending order, so A, C, E, G, and in the other half of the hypercube in ascending order from the end, so it's basically descending order. So B, C, F, H in the reverse order of processor numbers. So basically the sorting time on a Q-dimensional hypercube is the sorting time on the Q-1 dimensional hypercube, these half cubes, plus the time to sort a bitonic sequence. And because we determined that the time to sort the bitonic sequence is Q, the solution to this recurrence is order Q squared, or order log squared P. Okay, so very simple sorting algorithm and fairly efficient in terms of speed. It only takes log squared P or Q squared steps on a Q-dimensional hypercube. So here is the algorithm in action. So I already assumed that I've sorted this half sequence ACEG, this half sequence BCFH, communicate along dimension 2. So dimension 2 is in this direction. Dimension 1 is vertical. Dimension 0 is horizontal. Communicate along dimension 2, basically processor that has the smaller ID keeps the smaller of the two elements, and the one that has the larger ID keeps the larger element. So AH, they're already in order, so nothing happens there. Here, CF, similarly, are already in order. Here, EC are out of order. So C comes here, E goes there. And finally, GB, they're out of order. The processor with the smaller index should get the smaller value. So B comes here, G goes there. Then we communicate along dimension 1. AC, okay. HE are out of order. So we fix the order. CB are out of order. Becomes BC. And FG already in order. And finally communicate along dimension 0. EF, AB, okay. HG are out of order, so they become GH. And CC, they're equal, so they stay the same. So now the sequence is sorted from the smallest in processor 0, A, B in processor 1, C, C, E, F, G, H. Okay, so this is basically tonic sequence sorting on a hypercube with complexity order Q squared or order log squared P, where P is the number of processors. Okay, now that we have solved the sorting problem on the hypercube, we have at least one reasonably efficient algorithm for it. let's talk about routing problems. Recall that we distinguish various categories of routing algorithms or routing problems. Offline algorithms are the ones where the route is pre-computed and stored in tables. So I give you a routing problem, you have as much time as you need to pre-compute the routes, store them in tables, then when that particular routing problem arises, we basically use those tables to decide where and how to route. Online algorithms, messages basically go in the network and dynamically find their way through the network. So this processor that wants to send a message only decides where to send it on its first step, to send it this way, or this way, or this way, or this way. And then the next node dynamically decides where to send it next, and so on. So the nice thing about this online routing is that decisions can be made based on various criteria, such as congestion of nodes and unavailability of faulty nodes, and so on. In oblivious routing, the path depends only on the source and destination and nothing else. So if I tell you I want to send something from this source to this destination, the path is predetermined. Even though there may be multiple paths between those two nodes, one of those is chosen and is the path that is basically used by this oblivious routing algorithm. In adaptive routing, we can select from multiple available paths based on various criteria. Even if we decide to use only shortest paths, there may still be multiple shortest paths to choose from. Okay, so for routing in the Hypercube, we have good news and bad news. Good news is that any 1-1 routing problem with P or fewer packets, so if you have, say, 16 processors, P processors, and you have 16 or fewer packets sitting on these processors, each with a particular destination, we can solve this routing problem in order log P steps. So basically asymptotically optimal, because log P is the diameter of the hypercube, and therefore any routing algorithm requires worst case log P steps. We can solve such a problem in order log P steps. So it may not quite be log P, it may be a little bit more, but it's of the same order as log P, using an offline algorithm. This is a consequence of there being many paths to choose from, and therefore I can choose the paths for different messages so that as much as possible they don't conflict with each other. So that's the good news. But offline algorithms are not always favored. We may want to have online algorithms. And the bad news is that oblivious routing requires of the order of square root of P divided by log P time in the worst case. So if I restrict myself to the class of oblivious routing algorithms, when the path between any two nodes is predetermined. So for example, I use descent order for routing. Okay, so descent order basically says if I want to send something from here to here, first I route along dimension 3, go here, then along dimension 2, go here, then along dimension 1, dimension 1, and then along dimension 0 to get. So there's just one path available for this routing in this oblivious routing algorithm. Such an algorithm can be defeated. I can come up with a worst case routing problem that requires almost order square root of P, almost as bad as meshes. Okay, it's not quite as bad because it's divided by log P. but log p may be a small number, so almost as bad as meshes, even though I have many more links and many more alternate paths to choose from. If I restrict myself to oblivious routing, then the algorithm can be defeated. There's a worst case routing problem that requires this much time. Now, even though this is bad news for the worst case situation, in practice, actual routing performance is usually much closer to the log time best case up here than to the worst case. So on average, the behavior is not really close to this worst case, but closer to the best case. Okay. So here is basically a theorem that shows why that's the case. And the theorem is more general. It's not just for a hypercube. If you have a p-node graph with vertices and edges, so that the network is of degree d. In other words, each node has at most d neighbors. So in this case, d may be 5 in this diagram. Okay, this node v has 5 neighbors, and all the other nodes, none of them has more than 5 neighbors. This one has 4 neighbors, and so on. Okay, so if my network is degree d, any oblivious routing algorithm for routing p packets in G needs, in the worst case, at least square root of p divided by d time. Now, in the case of hypercube, the degree is log p. So this theorem, the special case of this theorem for hypercube, says that there's a routing algorithm that requires order square root of p divided by log p time. So how do we do this? I won't go through the details of the proof. The proof is shown here and in a bit more detail in the textbook that you can study if you are interested. So the basic idea is that a routing problem consists of p packets, each of them having one destination. Okay? So the possible routing problems that I can envisage, they're order p squared routing problems, because the packet that is in this processor may want to go to any of the other processors. The packet that is here may want to go to any of the other processors. So there are order p squared instances of routing problems. Okay, there are order p squared possible paths for routing among all node pairs. Okay, but the number of links that I can use is order p times d. There are p nodes, and each of them has d links. Okay, so p times d, actually p times d over 2 is the number of links. So those large number of paths, p squared, order p squared, use p times d links. So it's inevitable that many of those paths will be going through the same links. And it's always possible for me to identify k node pairs, UIVI, such that the starting points of the two, so these are paths basically, k node pairs are paths, so that the starting points of those paths are not the same, and the ending points of those paths are not the same. And choose those paths such that all of those paths pass through the same edge E. And I can make this k as large as square root of p over d. So if this many paths all have to pass through the same edge that can accommodate only one message at a time, so at most 2 messages if it's bidirectional, if this many messages have to go through that one edge, then of course in the worst case I need this much time to finish the routing problem. Okay, so this is basically a drawback of oblivious routing. But in the worst case, it has very poor performance. As I mentioned, all is not lost because the worst case may not actually happen very often. So it's the average case performance that is of greater importance to us. Okay, now in a hypercube, dimension order routing is very simple. It is an instance of oblivious routing, so bear in mind that it has some drawbacks, but it's very simple to implement. So here I've shown a route from node 5. So this is the hypercube, 8-node hypercube. This is the unfolded hypercube, which is basically a butterfly network. An unfolded hypercube is when all the dimension 0 links are placed here. All the dimensions, so basically each node is replicated. Node 0 is replicated. Node 1 is replicated. Dimension 0 links from 0 to 1 and 1 to 0 are placed here. And of course, node 0 is connected to itself, so that those are the horizontal lines. Okay, the reason I do this unfolding is that it's easier to visualize routing paths and this unfolded version of the hypercube or butterfly network than on the hypercube itself. Okay, so for example, if I want to send a message from node 5 to node 3 in the hypercube, I could do it here, but it's difficult to visualize where I should send it first. But here it's very easy. From 5 to 3, no transmission along dimension 0 is required. So I don't go here. I remain in node 5. Then dimension 1 transmission. Then dimension 2 transmission. Okay, this is because 5, which is 101, differs from 3, which is 011, in bits 2 and 1, and they're the same in bit 0. So because they're the same in bit 0, I don't need to move along dimension 0, but I do move along dimension 1 and dimension 2. So this red path here in the butterfly is a visualization of this path in the original hypercube. From 5, stay in 5. Well, stay in 5 basically means do nothing. Okay. Then send to 7. Then from 7 to 3. Okay. This is a bigger example in an 8-dimensional hypercube. So suppose the source node address is this binary string. The destination node address is this binary string. We compare the two strings and figure that they're different in bit position 0, bit position 2, 3, and 7. Therefore, we need 4 steps for routing because they're different in 4 bits. So let's say we do from the highest dimension, we do a descent algorithm. So change this 0 to 1. So go from this node to this node. Dimension 7 step. Then do a dimension 3 step. Change this 1 to 0. Then do a dimension 2 step. Change this 0 to 1. And finally a dimension 0 step. Change this 1 to 0. Okay, the nice thing about dimension order routing is that it's very simple, and basically all this node has to do is to decide whether dimension 0 routing is required or not required, then whether dimension 1 routing is required or not required. Then this node decides whether dimension 2 routing is required. Okay, I already mentioned this when we discussed the processor to memory interconnection networks in connection with shared memory. Uh, if you have a packet that wants to go from node 3 to 6, the hypercube, 3 in binary is this, 6 in binary is this. You XOR these two together and you get what we call a routing tag, 101. So this basically says that the two addresses are different in bit 0 and bit 2. Therefore, going backwards, we do need a dimension 0 routing step, no dimension 1 routing step, and we do need dimension 2 routing step. So 3 to 6, and this is the black path that you see here. Dimension 0 routing is required, dimension 1 is not required, dimension 2 is required. If I want to send from 3 to 5, the routing tag is 110, so no dimension 0, dimension 1, dimension 2. So no dimension 0, dimension 1, dimension 2. That takes us to 5. And the final example from 6 to 1, 6 XOR 1 is 111. So we need routing along all three dimensions. So from 6 to 1, dimension 0, dimension 1, dimension 2. And this one we also discussed in connection with shared memory, that butterfly is not a permutation network. Sometimes we get lucky and multiple paths that are required in the case of shared memory, or multiple messages being routed in the case of Hypercube. Remember, these are visualizations of paths, so we don't really go from, say from here, we don't go from a node to a node, it stays in the same node. So go from node 1 to node 0 and stay in node 0 for that message. Go from node 3 to node 1 for that message. Go from node 4 to 6 and 2 for that message. So all these messages go through different nodes and different edges, so they don't interfere with each other, whether we send them on a store and forward basis or wormhole routing. With wormhole routing, these worms never interfere with each other because they're going through different paths. On the other hand, I can get unlucky and have two messages that both go through 0. So this is a message, let's say, going from 0 to 4, which has this path, and another one goes from 1 to 0. Because our path is predetermined, these two actually conflict, and we can't avoid that conflict. In fact, in the worst case, there will be a lot of those conflicts. Consider a 2a plus 1 dimensional hypercube, basically an odd dimensional hypercube, and consider messages that want to go from nodes with this type of address. Basically, there are a plus 1 zeros, then a arbitrary bits. So there are 2 to the a such nodes, because depending on whether you assign a value of 0 or 1 to each of these variables, you get 2 to the a nodes. Okay? 2 nodes whose addresses are basically the bit reversal of the sending addresses. So the message going from this particular address goes from this address, which is the bit reversal of the sending address. So imagine 2 to the a different messages with these source addresses and these destination addresses. Now 2 to the a is approximately a little bit less than square root of p. Okay, if we have p is 2 to the 2a plus 1, our q is 2a plus 1. 2 to the 2a plus 1 is the number of nodes in this hypercube. And 2 to the a is basically square root of p divided by 2. So order square root of p. So I have order square root of p messages, all of which, if I use dimension order routing, basically, how do I do dimension order routing? Okay, I start, let's say, from the least significant bit, XA. If it's 1, I change it to 0 because it needs to go there. Okay, this one, if it's 1, I change it to 0. By the time I've changed all of these to 0, some of them already be 0, but those that are 1s are changed to 0s. I get to node 0. Okay, because all of these have been changed to 0s, and these are all 0s. So I'm at node 0. So all of these 2 to the a messages go through node 0 on their way to their respective destination. Therefore, there will be order square root of p messages that all want to go through the same node, and therefore the worst case delay is order square root of p. Notice that this is even worse than the bound that we established with the theorem we discussed earlier, which was order square root of p divided by log p for the hypercube. Besides delay, which is large, also large buffers are needed within the nodes because these messages tend to basically conflict with each other and will have to be stored when conflict exists. Now, if we limit nodes to a constant number of buffers, superficially, it may seem that this problem may be solved. So for example, let's say this node has just one buffer, but 2 messages are headed for it. Okay, well, we accept one message and store it in that buffer, and we block this message. Somehow, by giving feedback to this node, we tell it not to send this message. So maybe the problem won't be as bad because these messages wait, and therefore I don't need a large buffer. Unfortunately, that's not a practical solution. Oops. Okay. Because the delay can now increase from square root of p, large buffers, to order p if we limit the size of the buffers to 1 or a small number for some permutations. In other words, those messages that are blocked, there will be very many of them, and therefore potentially can increase the delay to order p. However, again, the good news is that performance is usually much better. So it's really of the same order as log 2p in many practical cases, plus these lower order terms. So the difference with this optimal is fairly small in practice for the average case routing problem. Okay, wormhole routing, I already discussed. It's the same problem. If paths are distinct, then worms will not interfere with each other. If paths conflict with each other, then worms will block each other. And we have basically the same disadvantage as in store and forward routing. Okay, the next idea is broadcasting on a hypercube. So an algorithm for broadcasting that is applicable to any network, any graph, that has all port communication. Basically, each node can send messages to all of its neighbors. Is called flooding. So what is flooding? Suppose node 0 in a 5-dimensional hypercube has a message to broadcast to all the nodes in the hypercube. Now this node 0 has 5 neighbors. These are the 5 neighbors. Okay, flip node, flip bit 0, flip bit 1, flip bit 2, flip bit 3, flip bit 4. These are the 5 neighbors. So this node sends the message it wants to broadcast to all 5 neighbors. Remember, I'm assuming all port communication. Okay, then each of these 5 neighbors also has 5 neighbors. Of course, one of them is this node, so it has 4 other neighbors. So it will send a message to those 4 neighbors. So in Q steps, every single node in the Hypercube has received that message. So we have completed the broadcasting in the shortest possible time, which is Q steps. Unfortunately, there are 2 drawbacks to this algorithm. One is the requirement for all port communication, which may not always exist. And the other one is duplication. So consider, for example, these 2 nodes. One neighbor of this node is 11000, flip this bit. And one neighbor of this node is also 11000. So these 2 will be sending the broadcast message to that shared neighbor. So there are duplications in messages that basically require more communication than absolutely needed. And also because communication consumes energy, more energy will be consumed. So it would be nice if we remove this all port communication requirement and also remove the duplications from this flooding algorithm. And we can fortunately do that while keeping the minimum Q-step communication time through what is known as binomial broadcast tree, which requires only single port communication. So this basically, this diagram shows the communication scheme. Node 0000 initially holds a value. It sends that value to just one of its neighbors, which is 10000. This is basically the neighbor of this node in the other subcube, whose node labels start with 1. So initially, one node knew what the broadcast message is. Now 2 nodes know what the broadcast message is. In the next step, each of these nodes in turn sends the message to one neighbor. This one sends it to its dimension 3 neighbor. This one also sends it to its dimension 3 neighbor. So now 4 nodes know the message. So we started with 1, 2, 4, then 8, then 16, then all 32. So it needs 5 communication steps, 1, 2, 3, 4, 5, the best possible. Okay, each node over each time step just sends one message to one neighbor, and there are no duplications. Each node receives the broadcast message through this unique path that leads to it in the binomial broadcast tree. Okay, so this is a very efficient algorithm and very easy to implement. So basically, there are 2 classes of nodes, those who already know the message. Initially, only this one knows the message. All the other nodes are marked as not knowing and communicate along dimension 5 by nodes that already know the message. And then this one is marked as knowing the message, and communicate along dimension 4 by nodes that know the message. There are 2 of them right now. Okay, so it's very easy to program, write the algorithm. Okay, these diagrams show a couple of other ways of communicating. So the top one is the binomial broadcast tree. So the message ABCD, that's a long message, let's say, consisting of 4 packets, is sent from this node to this node. So from the lower subcube, the upper subcube, just one neighbor. Then This node broadcasts in the lower subcube, this node broadcasts in the upper subcube. Sending along the next dimension, then these 4 nodes now know the message. They broadcast along this dimension. Now the 8 outer nodes know the message. And finally, the outer nodes send the message to the inner nodes, and we are done. So that's binomial broadcast tree. We can pipeline the message transmission. If the message is long, like ABCD, instead of sending all of the message from this node to this node, we just send one packet. And as that packet goes on its journey, the next step, we send the next packet, B. Then as A goes to the next step of the journey, B goes to this step, C will be transmitted. Okay, so this requires all port communication. So even though it saves time because we are pipelining the broadcast, in this step, for example, you see that this node is sending A to this neighbor, sending B to this neighbor, it's sending C to that neighbor. So it has to have the ability to communicate with multiple neighbors at once. Whereas in the original binomial broadcast tree algorithm, there was just one. Each node communicated with one neighbor at a time. Okay, this one, because you may hear about it in various books and papers, Johnson and Ho's method, is even less practical than this one. This one basically says, why send the packets in order? First A, then B, then C, then D. Let's basically, if we have all port communication, let's form multiple binomial broadcast trees, one for A. So A starts its journey through this dimension, B starts its journey through this dimension, C through this dimension, and D through this dimension. In the next step, A goes on to this dimension, B goes from this dimension to, B goes, which went along this dimension, the diagonal dimension, first, it now goes in this dimension, and so on. So each of these pieces of the message, each packet, goes through its own binomial broadcast tree, but then you see here that nodes basically have to be able to send messages to all of their neighbors at once. So I didn't even bother to draw all the paths here because it becomes quite messy. So I've only shown the last step for packet A, which is the same as this. The last step for packet B would be along another dimension, and so on. Okay, the last section in this part deals with adaptive and fault-tolerant routing. As we saw in the case of mesh-connected computers, adaptive routing creates the danger of deadlock if we use wormhole routing. And wormhole routing is basically the routing method that is preferred in parallel computers because it uses resources efficiently. So we are interested in avoiding deadlocks. Dimension order routing automatically avoids deadlocks, but it's not as efficient as it could be because it uses predetermined paths for each source destination. So what's the solution? Well, this one possible solution is if we have a network, such as a three-dimensional hypercube shown here, but the method is quite general, we can divide the network into, let's say, 2 subnetworks. And again, more generally, we can have multiple subnetworks. Okay, in this example, I've divided the hypercube into these 2 subnetworks, subnetwork 0, subnetwork 1, by taking these bidirectional link and keeping one of them in this subnetwork, the one that goes from a smaller index processor to a larger index. So 1 to 5 is kept in subnetwork 0, 5 to 1 is put in subnetwork 1. Okay. Similarly, 0 to 2, smaller processor to larger, smaller index processor to larger index processor is in this subnetwork. 2 to 0 is in here. Another example, 2 to 6 is in this network, 6 to 2. So this is the criterion that I've used. So a link is kept in subnetwork 0 if it leads from a smaller index processor to a larger index processor, and in subnetwork 1 if it leads from a larger index processor to a smaller index processor. Okay? Then I agree to route messages from, let's say, 4 to 3. Processor 4 to 3 is, let's say this red dashed line is indicates the message source and destination. So my routing algorithm basically utilizes this subnetwork for a while. Then it shifts to this subnetwork, and then it utilizes that subnetwork, never going back to this subnetwork. Okay, that's a requirement for the algorithm. And the reason for that is that this subnetwork is acyclic. In other words, doesn't have any cycles. This subnetwork doesn't have any cycles. And the transition from one to the other doesn't create any cycles, okay, if I don't go back. Therefore, all the paths are guaranteed to be cycle-free, and therefore there will never be circular waiting between messages, okay? So if I want to send from 4 to 3, okay, let's say I can go from 4 to 5 and 5 to 7. Okay, I can't get from 7 to 3, but I switch to this subnetwork. I go from 7 to 3. So that's one possible path. 4 to 5, 5 to 7, and then 7 to 3. Okay, is there another path? Yes. 4 to 6, 6 to 7, then go to this of 7 to 3. So even though I'm losing some of the paths, so for example, in the original Hypercube, I could go from 4 to 0, 0 to 1, and 1 to 3, that path is no longer an option. Okay, because I can't go from 4 to 0. If I switch to this subnetwork, I can go from 4 to 0, but then I can't get out of 0 towards my destination. Okay, so some paths are eliminated because of this scheme that I've chosen, but I still have occasionally multiple paths, and I can use an adaptive algorithm without worrying about the possibility of deadlock. Okay, what about faults? Whenever we have a large parallel processor with many nodes, we should consider the possibility of faults. In this case, of course, I've shown a small hypercube of 16 nodes, but the concepts are the same. So imagine that this node has all 3 of its neighbors faulty. Sorry, 3 of its 4 neighbors. So this one is faulty, this one is faulty, this one is faulty. There's just one non-faulty neighbor. Of course, if this neighbor were also faulty, then this node will be isolated from the rest of the nodes, and therefore that's undesirable. So let's say in a 4-dimensional hypercube, we limit the number of faults to 3, so that no node can potentially be isolated from the other nodes. I can still route from this node to any other node, any other healthy node, by first going in this. So the first step of the routing is forced. I have to go here. Then from there, I can take different paths. So from source to this destination, I can take this path, 1, 2, 3, 4, 5 steps. Remember, in the original non-faulty hypercube, I could get from any node to any other node in no more than 4 steps. And in fact, I could get from this S to D in only 3 steps. 1, if this weren't faulty, 2, 3. Okay, it has been proven that when a hypercube, two-dimensional hypercube, has up to q minus 1 faulty nodes, its diameter in the worst case increases by 1. In this case, you see that the diameter has increased from 4 to 5, and we call that the fault diameter of a particular network. So the fault diameter of the hypercube, two-dimensional hypercube, is q plus 1. Where fault diameter means the diameter under worst case q minus 1 node faults. Okay, so we can define the notion of fault diameter for other networks. So for example, if I have an 8 by 8 torus, I may ask, okay, what is the fault diameter? An 8 by 8 torus has a diameter of 5, if I remember correctly. And therefore the question is, a torus, each node has 4 neighbors. What is the worst case pattern of 3 faults? And does it increase the diameter from 5 to 6 or 7 or 8? So what is the fault diameter? And this question, basically, people have studied for different kinds of networks. The smaller the fault diameter, the more resilient the network is. In other words, its performance will not be affected by much if the fault diameter is only slightly more than its original diameter. Okay, so that's all I wanted to say for this chapter 14. In this lecture 14. In lecture 15, we will cover chapters 15 and 16 of the textbook. I will sample some of the topics because there won't be enough time to cover everything. So until then, please stay safe and goodbye until the next lecture.